This is lecture 28. So in the previous lecture, we were discussing about how to make inductors in an integrated circuit, and we talked about some of the pros and the cons, and what are the issues that one might face in while designing inductors. So what I'll do in this lecture is talk briefly about, and I'll tie up some of the loose ends of about the inductors, and then move on to capacitors. Right. So if you recall, the inductor structures that I had talked about were, without really mentioning it explicitly, were something like either this or and then you take the ports out somehow, right? Through a via or through a where and so on, right? So the important thing to note here is that you are not able. I have not drawn a circular structure. I have not drawn anything which is like this, even though this might be the most optimal structure for an inductor, because if you have spirals, if you have actual circles, then the current has a smooth way to flow and you do not have current crowding at the edges and so on. But the problem is in IC design, the PDK or the process design kit that you will be using, it will never, almost never allow you to draw a circular, a clean circular metal strip. So in most cases, they will either say that you have to limit yourself to 90-degree turns, or in some cases they might give you for some leeway while designing inductors, and say maybe some specific 25-degree turns or 45-degree turns or 22.5-degree turns are allowed. Now, depending upon which technology you are using, you will have to see which particular geometry you can suits your technology. The second important thing to note is that even though I have kind of bypassed this discussion, how do you take the contacts out from the middle of the spiral? So if you have to take the contacts out from the middle of the spiral, then obviously you have to dig a via, right? Once you dig a via, then now depending upon, so what you have to dig a via, go to the lower metal layer, and then go underneath and then come up, right? Now, as it turns out, in most processes, in most RF processes, the top metal layer has the maximum thickness, which means it has a minimum resistivity, and the lower metal layers have lower thickness, and they have higher resistivity. So, moment you go to a lower metal layer, and you take the signal out, like the way I have shown here, you end up having more losses, correct? So when you have more such resistive losses, you have a problem. So the structure that I have shown here that's why it's not a very optimal way of doing a layout, doing an inductor layout. Another problem of these structures is that when you draw a loop, how do you get, what is the genesis of the inductance? Is basically the flux that is cutting the area of the loop, right? So larger the area, more the inductance. Now the whole purpose of having these concentric loops is to basically say that I will have multiple of these loops, and the inductances will couple, and the fluxes will couple, and I'm going to get larger inductances, right? But the problem is that the center loop, as you can see, obviously has a very small area with respect to the outer loop, correct? But the effect of this current crowding and skin effect and all those things are still present as much in the inner loop as in the outer loop, right? So that is why, and also these interturn capacitances, these will also be present as much if in the inner loop as in the outer loop, correct? So the problem is, now all the bad things are present as is if you have multiple turns, like the way that I have shown here. but the good things are not as much if the inner loop becomes smaller and smaller. So that's why in unless you are okay with some amount of loss, right? So these type of structures are not always encouraged, right? So it is better to have if you are looking for inductances with lower loss, then it is better not to have a very small spirals inside, and maybe have one or two turns at the two big turns at the outside, and let it be. Okay. Now the problem with that is that it you take up a lot of area. Now that's a design call, right? Whether such an area can be is acceptable or not, right? So but having said that, there are structures which are not as which are more definitely more area intensive than these structures, but slightly better with regards to not using multiple turns or using only one turn. Let me show you one. So let's say I have one structure which is, let's say your input comes in through here, and you want to take the output from here. So that way both the feed lines also have similar routing, right? In the two structures that I have shown on the top, the input and the output are not, taken out symmetrically, and one of the feeds probably will have higher resistance, more losses than the other. Okay, so what if I make a structure like this? And this also, so you can have multiple of these angles. For the sake of brevity, I am showing only 3 of these strips. Now while going from now at when the signal goes to this, it comes at this point, I maybe go to a lower metal layer and quickly come up instead of having a big turn, right? What I mean is, let's say I have another routing inside like this, and this is connected through a lower metal via like this, correct? Similarly, this structure gets completed by going here and coming out, correct? So that way you see that now, depending upon what are the thickness of these lines, this part of the inductor which has a via which goes down, right? Might not, it will not have as much extra routing as with respect to these two structures, correct? That should be readily evident. Okay, and the other important, and note that in this structure also you are kind of keeping the current direction the same, right? Through the adjacent turns, so that they do not go and cancel out the fluxes, right? So essentially the sense of the current, sense of the loop remains the same, and this structure also has a sense of symmetry through the center point, right? Also can give you decent amount of inductance without lot of loss, right? Okay, so this type of structures, that's why sometimes are also preferable. There are some other, as you can readily guess by now, is that this is essentially a geometry problem, and depending upon what type of process that you are using and what type of losses you have in the processes, you can have structures which are one structure which is good in one process might end up being not so optimal in another process, and so on, right? So that is why whenever you have a process design kit, you need to and you know that you are going to use inductors, so it is better to characterize the type of inductors that give you decent performances, and then go ahead with it, right? So we saw some in the previous lecture. I talked about some models of the inductors, right? Those models are useful to characterize how good or bad an inductor is, but there are some other simplistic models that also you can use to give a not so accurate but a ballpark estimate as to how to understand how good or bad an inductor is, right? So for example, I mean, the inductor model that I showed you in the previous lecture was something like this. So this is your main inductor. You have lossy R's here, and these lossy R's can be the series resistance, physical series resistance, or due to skin effect, or due to proximity effect, and so on. They are lumped into this resistor. And then you can have some substrate coupling and the resistance of the substrate also contributing to some loss. So at this point of time, I should also maybe put in a word that if you are using processes which are depleted, that is, for example, fully depleted SOI and all, then you do not have to deal with these R subs, right? So that is why in those processes, the inductors have a better performance than bulk CMOS, where the losses tend to be higher. Okay, so that's why you will see that many RF processes, if you tend to use FDSOI kind of technology, but the flip side is FDSOI is extremely expensive. It is much more expensive than bulk CMOS, right? And uh, I mean, that is one of the reasons you will have to make a design call, or this is the economic call, as to whether you want to pay up for that extra money, or you design something in CMOS, right? Okay, so let's continue this discussion. So this was one kind of a model which I showed you in the previous lecture, that which can be used to model an inductor. But still, this model is slightly complicated, and the example that I took while characterizing an inductor with regards to loss was, I assume that you're working in a very high frequency. All these capacitors are, especially this C sub and all, are shorted, right? Or do you ensure that you use your inductor for maximum efficiency per se, right? Even though I have not yet defined what is the main characteristics of an inductor per se, right? Okay, so what I am going to do next is to show you a even more simplistic structure of this inductor, right? Which will probably give you another idea of how to think about uh, uh, designing an inductance, right? So for example, so if I assume that the C sub is small, right, a very cut down version of this, a simplistic version of this structure will be something like this. You have an L, you have some R, some lossy R, let me call this RL, and you have this capacitor, right? So between these two ports, A and B, ideally I would like to see the impedance of this between these two ports to be j omega times L, right? But we have RL and we have C, right? So even if, let's say, we neglect RL for the time being, right? So if we neglect RL for the time being, what are we going to see across A and B? So the impedance that I'm going to see is j omega L times 1 by j omega C by j omega L plus 1 by j omega C, which is nothing but j omega L by 1 minus omega square LC. Now, if I plot this, right, if I plot this, what would I see? If I plot j, let's say I plot CAB by j omega, right? if I plot ZAB by J omega, what would I see? I would see that, or simply let me say ZAB, and this is entirely imaginary, so I do not have to really plot by J omega, right? So if I plot this, so what would I see? So let's say I am plotting the imaginary part of ZAB. So I should see at very low frequencies this increasing linearly, right? But at omega equal to 1 over under root LC, what would I see? So at omega equal to under root LC, I would see this impedance to go to infinity, right? So this impedance will go to infinity, and then at frequencies higher than 1 over LC, under root LC, what I'm going to see? It is going to start from minus infinity and come like this, right? And at omega tends to infinity, everything will converge to 0, right? So what I am saying is this one is approximately equal to j omega L for omega much less than omega naught. J omega naught is this, and is approximately equal to, if I am operating at omega much higher than resonant frequency, this omega square LC term will dominate. So omega L will cancel, so you will end up with 1 by j omega c, 1 by j omega c, or in other words I can say this is minus j by omega c, correct? So this is at omega much greater than omega naught. So here in this region your impedance looks like an inductor, so this is inductive, and in this region your impedance looks like a capacitor, right? So note that I'm only plotting the imaginary part, right? So don't get confused with the fact that how come I have negative part, right? So the negative comes because if you multiply j, if you take the capacitance impedance as 1 over j omega c and you multiply with j, so if you do imaginary part, which means you have to multiply with j in the numerator and in the denominator, so you get negative j by omega c. That's why that negative curve is coming. But the key point to note is that this part of the curve is capacitive, right? So your contraption, so this is omega equal to omega naught. Your contraption of which is supposed to be an inductor is ceases to become an inductor beyond the resonant frequency, right? And there is an important name for this. This is called a self-resonant frequency, right? So this frequency is often called self-resonant frequency, or SRF. So if you see data sheets, many data sheets are going to quote this number of SRF or any inductor that you see. Even if you see an Opchif inductor, a discrete component, you are going to see a terminology and the SRF is 1 gigahertz or 500 megahertz or 10 gigahertz or whatever. That essentially means that below that frequency, your inductor is going to behave like an inductor. Above that frequency, it becomes a capacitor. So naturally, when you are choosing your components or designing a component, obviously you will have to ensure that you plot this imaginary part of your inductor or supposed imaginary part of this inductor and see at what frequency your inductor ceases to become an inductor, right? Otherwise you are going to face a lot of problem, right? Okay. So the formal way of defining the quality of an inductor is called the quality factor or the Q factor. And there are, if you look into the literature, there are multiple definitions of Q factor for an inductor. You can stick to one of them. Each one of them have their own merits and demerits. But typically, the one that, in my opinion, is most useful is basically the imaginary part of Zn of the inductor divided by the real part of the Z in, right? So, so ideally, what you want this Q to be? Obviously, you do not want any real part to be in the Q, right? But what is the source of the real part? The source of the real part is that this lossy in resistance uh, that invariably comes into picture. And as we have done as we have gone through the previous lecture and part of this lecture, you saw this is not the only resistance part also, right? There are other resistors associated with it, right? So you have so many other sources of losses, and not only due to the current flow through the inductance, but it can go into the substrate and coupling losses and so on. So all of them, let's say I am able to lump into RL, which is strictly not correct, but let's assume that this at a particular frequency I'm able to model it like that. Then clearly, if my inductor model is only like this, then clearly it makes sense that if I keep on increasing the frequency, right, your Q factor, the quality factor will increase, right? Because the imaginary part is omega L and the real part RL is supposedly constant, so Q will increase. But we also know that it is not supposedly constant, because RL has components of skin effect, which also increases the frequency, but with under root F. It also has an effect, as a proximity effect, right, which has slightly, even though I did not give you the formula, but if you simulate it, or if when you design, if you characterize your losses, you are going to see that the effect of proximity, the resistance to the proximity effect also increases faster than that of skin effect, and so on, right? So even though this simplistic model tells us that if you keep increasing the frequency, your Q factor will increase linearly, that's not true. That it might, I mean, it will increase and it can saturate, right? So if you recall one of the curves that I showed you in the previous lecture, right, where I had neglected all the inductances, all the capacitances, and I had kept only the when I said I neglected, I mean I assume all the capacitances are shorted other than the main capacitor. So if I neglect this capacitor and assume C subs are shorted and all, you get this L and R sub and all, right? So one example that you can readily figure out is that at sufficiently high frequencies where both the L and the series resistances give higher impedance than R sub, then the current would choose to go into R sub and not into L, right? So in that, eventually you are going to have a degradation in the Q factor. So even though this simplistic model is kind of telling us that at very high frequencies, Q can be very good, that's strictly not true. But having said that, if you when you start from very low frequency and you keep increasing the frequency, your Q tends to increase. And perfectly designed inductor, for a perfectly designed inductor, you would like to operate it at the position where, or at the frequency, or you would like to design your inductor in such a way that you get the maximum Q at the frequency of interest. Correct? The other thing that obviously that you should keep in mind is, obviously we have this capacitor also, right? So that will also give rise to a self-resonant frequency. And as you can see that depending upon where you would want to, you would want your inductor to behave like an inductor, or you want your inductor to behave like a capacitor. Obviously, you would like your inductor to behave like an inductor. That goes without saying, which means that you have to ensure that you are kind of slightly away from the self-resonant frequency, or significantly away from the self-resonant frequency as the need may be, right? So these are some of the things that you should keep in mind while designing an inductor. So the crux of the matter is that you design an inductor, you find out its imaginary part, you find out its real part, and you plot its impedance, and then see where the self-resonant frequency is, or you plot the Q and find out what is the best place to what is the sweetest point to operate an inductor at, and then you keep tweaking your design, right? If, for example, if you see your self-resonant frequency is is lower than anticipated, right? So what design handles are you going to use? So what is the cause of self-resonant frequency? The main cause of self-resonant frequency, it seems, at least in this model, is this capacitor, right? The capacitor between the terminals of the inductance, correct? So even though I have shown a capacitor between the inductance, but effectively that is a distributed capacitance between the turns, right? You have these distributed capacitances, or even here you have these distributed capacitances between the turns that is giving rise to that capacitance that I have lumped into. And if your self-resonant frequency is lower and you want to make it higher, right? Let's say you designed your inductor and you found out that the self-resonant frequency is 10 gigahertz, right? But you want your self-resonant frequency to be 20 gigahertz, which means that, I mean, all the easiest handle is to ensure that these capacitances, these interwound capacitances are smaller, which means that you have to physically space them out, right? Which means area penalty, right? So that essentially it. Moment you want to make a very good inductor, you have to pay with area, right? So that's one of the problem. That's one of the reasons why, in general, IC designers tend to avoid inductors as long as you cannot avoid it anymore, right? When it's required, you pay up with the area and you go ahead with your design. Okay, so far so good. So far we have talked about how to go about designing an inductor. Again, I mean, designing an inductor is again a massive. I mean, if you look into the literature, there have been papers which have focused on only designing of inductors. I gave you a very brief 1,000-feet overview of what are the things to look out for. Right now, you can come up with novel geometries which can optimize the design of an inductor based on reducing these unwanted elements. But by no means whatever I told you is exhaustive. And also, I have not told you anything till now about how to design a transformer. If time permits, later on in the course, we'll be talking about PAs and all. I'll try to give you a brief primer about how to take care of transformers and some of the curious things, interesting things that comes about from transformer design. So the next thing that I would like to focus in today's lecture. So let's put an end to the inductor because I have to stop somewhere. So next thing we should like to let me focus on is how to go about designing a capacitor. Now, what is a capacitor? It's probably one of the simplest electrical elements that you can get. And you have two metal plates. You put them very close by. You have which means that you have electric fields which will be confined between the two plates, and you get a capacitor. Closer the plates, but higher the capacitance. And fortunately, in IC design, you can get metal plates to be very close to each other, simply because they are. I mean, we are talking about extremely small geometries, right? So that is one of the reasons IC designers love capacitances, because getting whatever you have to do to get a good capacitance is probably not the same thing as you have to do. Probably conflicting with respect to whatever you need to do to get a good inductances, right? So let's see what are the ways of designing a capacitance. Now, already you have seen the metal stack. There are so many metal stacks that are available to us. So now let's talk about capacitance, right? So you have already seen you have metal stacks. So let me redraw the metal stack. Maybe again, this is P minus substrate, and you have maybe metal 1 here. Then you have a metal 2 here, and in between you have oxide. Then you have metal 3 here, and you essentially means that you get capacitances between them if they are sufficiently close by, right? And if you want larger capacitance, you make a bigger plate, and so on, right? And that's as simple as it can get, but there are issues. I mean, should not be any surprise that we have issues about with almost everything. But what are the issues? So now let's concentrate on this structure, where let's only concentrate where we have M1 and M2. So as you can see that if you have to feed a signal, somehow you have to feed a signal into M1 through here, and you probably will take it I mean, you'll connect something to M1 through here, right? Uh, and then maybe there are vias, you take the signal up or down depending on wherever you want to go. But note that what is happening is there is a parasitic capacitance between this M1 and the substrate, right? There is also a parasitic capacitance between M2 and the substrate, correct? But this value of this parasitic capacitance between M1 and the substrate and the M2 and the substrate are not the same because M2 is sitting physically at a higher distance from the substrate than M1, right? So this capacitance, let me call this CM2 and this is CM1. So naturally CM2 will be grounded, let's say. Bulk is grounded. CM2 will be less than CM1, right? So you wanted a capacitor which is maybe you wanted a capacitor between two nodes. Let me call this VA, VB, right? So now what you end up getting is also capacitors to ground, CM2, CM1, correct? This might not be a problem if you are looking for a grounded capacitor, right? So if let's say VB is supposed to be grounded, then what happens? If VB is supposed to be grounded, then this CM1 comes in parallel. This CM1 doesn't matter because this is anyway grounded, so this goes off. This CM2 comes in parallel to C and it adds up to C, right? No issues. So this is grounded capacitance. Then you don't have a problem, right? So in that case, probably it's okay. You don't have a problem. This might be even better. But if you are looking for floating capacitor, right? Like you in most RF applications, you want to couple an AC, you want to AC couple a signal from one point to another while the DC bias is set, right? So in that case, you do not have a grounded capacitor, you have a floating capacitor. So in that case, this type of structure can be problematic because you're ultimately, let's say you are wanting to do a floating capacitor through here, and maybe you have a signal that comes through this side. So the signal is supposed to, you have chosen a very large value of capacitor C, which means the signal is supposed to get coupled from here to there. But right now, because of CM2 and CM1, it can also get shunted to ground, right? You can have a loss of signal, correct? So the problem is potentially can lead to signal loss. Correct? So this can lead to signal loss. So now, and this can be also be a problem if you want symmetry of operation between either plates, right? We have not really looked into those applications where you would want symmetric operation between the plates of the capacitors, but in certain applications that can be a problem. But I mean, let's leave it at that for the time being. But this at least is you should be mindful of the fact that if you choose to use capacitances between multiple metal layers, then you might end up not only with capacitances. I mean, you might end up with capacitances which are not uniform from between one metal and the other, right? The other thing that you have to keep in mind is that lower the metal layer, higher is the parasitic capacitance. I mean, that's obvious because lower the metal layer, closer you are to the substrate, so you have higher parasitic capacitance, so you have a more loss. So if you and in this case, what is the loss? The physical loss mechanisms are your substrate has a resistance, right? Your substrate has a resistance to ground. So essentially, so you have this loss, right? You have this extra resistance, which can also contribute to noise and so on, right? So so that's a problem. Okay, so but fortunately there is a solution, which is, by the way, this This type of structures are called metal on metal capacitors, right? You have one metal layer and then an oxide and on top of metal. Uh, but even though we are used to drawing capacitors like this, if you look at actually the metal stacks in IC design, as it turns out, the side walls are quite thick, right? So it's the side wall. So if I draw a metal layer, if we actually draw a metal layer, not necessarily to scale, it can look like this. So your metal layers can look like this in an IC. So let's call this, I don't know, maybe M2, and let's call this M1, right? So the capacitance that we were talking about here, this capacitances that we were talking about here actually is this capacitor, right? Now you might say that I can make the brick wider. I have shown you for, I mean, a slightly smaller width of the metal, right? I mean, now depending upon technology to technology, this exact geometry can change. But this is to give you an idea about if you just go with the default setting, you might end up you might end up invoking capacitance like the way I have shown you. But the reason this might be an exaggerated picture, but the reason I showed you this picture is because readily you should be, I mean, something should click in your mind that there should be another way of realizing a capacitor, and that might be two metal two lines. So that is, say I have one line here and maybe another metal two line which is placed nearby. Correct? And you are going to have, if they are sufficiently close, you are obviously going to have capacitance between these two plates and so on, right? And if they are elongated, you can get a lot of sidewall capacitances, right? So this can be one signal. I mean, this can be VA and this can be VB, and this is basically your capacitance between VA and VB. Correct? And depending upon, now you can make spirals of this like an inductor, right? So you can make one. Now if I go to the top layer, let me draw a top view of it. So if I am drawing a top view, something like an inductor, so let's say this is VA, this is thick metal line, and maybe this is VB. Let's say this is VB, right? And you get this one intervene capacitance between the same metal layers, right? Both of them, let's say this is M4, this is also M4. Okay, so you kind of get interdigitized interlocking capacitances. This type of capacitances are called MIM capacitances or MIM capacitances. Now note that if both of them are at the top layer, at the top metal layer, so obviously you are still going to get a capacitance between this top metal layer and the substrate. But if both of them are at the top metal layer, firstly you are going to get the minimum possible capacitance between the metal layer and the substrate, and additionally this extra parasitic capacitance, which while being minimum will also be identical. This is C, if this is CM1, this will also be CM1, right? So that so this often also helps in getting in reducing the loss, because now both the metal layers can be at the top layer, right? Now you can do some more optimization of this loss. Now note that all these losses are referred to the substrate loss, right? Because that is the main source of loss in a capacitor, because the electric fields, right, from the bottom plate or the top plate, the fringe electric fields can can also, effectively you end up having another place where the electric fields get terminated, and which means that, if your displacement current can flow through that electric field, that electric field can give rise to displacement current, which essentially is coming from the source, which means leakage and loss, right? So the whole purpose of capacitor design is to ensure that this loss comes to a minimum, right? So what happens, let's say, now I'm showing you, let me show you an example of with using a metal metal on metal capacitance option itself. So you have this, and let's say you have this substrate P minus. Let's say this substrate is not P minus, if this is a perfect insulator, right? So let's say, or in other words, I'm saying if there is no carriers, no mobile carriers, then can you comment on if this capacitor will be of any significance? No, right? Because if there are no mobile carriers, even though there can be an electric field, that electric field will probably get terminated long way back, and which essentially means that its capacitance will probably not be, if at all, will be very small, right? So this capacitance doesn't have any role to play, which means that that is a good thing, right? So that is one of the reasons fully depleted SOI processes are good for RF design, because you get, you do not have to deal with this P-type substrate. But having said that, even if you are using a P-type substrate, there is something that you can do, and that is as follows. So let's say you, for the sake of argument, let's say you dig up a N well here. Okay, let's say this is an N well. Okay, fine. And then what I do is I reverse bias this N well. I put this N well to VDD. So you might be wondering, what can I achieve by doing this? If you only do this, you will not achieve anything, right? Because, okay, fine, this diode is reverse biased, but still, instead of having P-type carrier in underneath my metal, I have N-type carrier, right? I have electrons here, correct? So I have not achieved anything, but note that if I have this parasitic capacitance, let me call this CP. So I probably should have had called it CP in the earlier pages also. So let me call this CPM. This is CP. This is also CP. Let me call this CPM2, CPM1. Okay. So if you simply do this, nothing is going to happen. You won't get anything, because whenever let's forget about this top metal for the time being. It is not useful for any discussion purposes. So if there is a swing here, there will be a swing here, and your displacement current will kind of flow through this, right? So there is no benefit. But what if now, instead of directly connecting it to VDD, I put a large resistor and then connect here to VDD? What purpose will this serve? So this will serve the purpose of, now if there is a swing here, there is a voltage swing here, sure, there will be a voltage swing here, but where will that current flow? Where will that displacement current flow? Can the displacement current flow now into this path? No, because I have a large resistance connected to VDD. This is a high impedance path, so your displacement current cannot flow into this path. Can it flow into P-type? So can it flow here? No, it cannot, because I have a reverse bias diode there. Correct? So it looks like by playing this trick, I have been able to I have been able to make the substrate high impedance, right? And this works. This works to a large extent, but it stops working beyond certain frequency, and the reason is this. This is a well, right? And this is a reverse bias well. So you have a depletion region here. So you have a depletion region here. So when you have a depletion region, you have a depletion capacitance. So you have C depth to ground, right? Now, depending upon how big the well is, your depletion capacitance can be big or small, right? So effectively now, instead of having CP to ground, right, you are having, if I call this V, it's a VB, right now the model becomes VB to CP to C depth to ground, right? And maybe you have some resistance and all, right? But having said that, this is better than having CP to ground, right? So that is why you get smaller parasitic capacitance, because now CP is coming in series with C depth. Now, depending upon how big or large is CP, if C depth is significantly smaller than CP, then you get significant benefit. Else, you probably get 50% benefit and that benefit and so on, and that is also not so bad, right? So this is something that is again is routinely done. Now, before I stop, couple of things that you should keep in mind. These CP, the question that you should have in your mind is the parasitic capacitance related to the choice of the capacitor, right? So is CP related to C? Right? What is C in this case? The C is probably if I choose to use the on metal capacitor, this is VA and this is probably VB. So this is the C. So is C related to CP? Absolutely. Because how do I increase C? I increase C by increasing the area, and moment I increase area, the parasitic capacitance also increases. So CP obviously also becomes proportional to C. Right now, typically it can be 1%, 2%, 5%, depending upon how good or bad the process is or how good or bad your layout is. Right. So, but it will never be zero. Right. But by playing these kind of tricks that I have taught, that I have shown here, you can significantly reduce the effect of the parasitic capacitance, right? Okay, so that is as far as the parasitic capacitances are concerned. What about resistors? I have not talked about resistors at all. So as it turns out, fortunately, in RF circuits, resistors are a bad thing, kind of, in most cases, right? Because they give rise to a lot of noise, and you do not want to use very large value of resistances unless you are using it for decoupling or AC biasing or DC biasing, AC coupling or DC biasing purposes. So if you are an analog circuit designer, you would pay a lot of, for example, you are designing DACs or ADCs, you pay a lot of attention to design of how to lay out a resistor. In RF circuits, it is still used, but they do not get that much of importance as far as the layout is concerned. But having said that, there are some best practices for resistors which we should always follow. So before we go there, so what are the types of resistors we get in an IC? Number one, you get a metal. A piece of metal has a resistance, right? Number two, you have polysilicon, right? Number three, you have N-well, right? And then you have, obviously, you also have P-type, you have P-well resistances, right? So among these, obviously, the metal gives you the least resistivity, right? And as it turns out, the N-well gives you the highest resistivity. N-well or P-well, depending upon which process you have. It gives you the typically I wouldn't put P-well because for that you will require a triple well process. But let's forget about the P-well. Typically you get metal, polysilicon, and N-well, and some combinations of these, right? So generally metal gives you the lowest input resistance. It's the lowest. This is the highest resistivity, and this is metal, right? So if you have to design for if you are shooting for hundreds of kilo ohms of resistances, or even tens of kilo ohm of resistances, N-well resistance is something that that is often preferred. Somewhere in between, I mean, maybe a kilo ohm or lower, you use polysilicon. Metal resistances are hardly ever used unless you want, for some reason, you want a specific reason, 10 ohm resistance or 20 ohm resistance or something like that. Other than that, metal resistances are hardly ever used. Now, having said that, there are certain things that you should keep in mind. All these resistances also vary with temperature. Now, good thing about, now if I go back to the discussion on inductors and capacitors, they don't really vary with temperature. Like to the first order, they do not vary with temperature, simply because I'm talking about electric field and magnetic field, right? As long as you have currents, you maintain a steady current or steady voltage, they don't really change. But how are resistors made? Their resistors are made, I mean, the core principle of making a resistor is you have a lattice, right? You have some piece of silicon or a piece of material, you have a lattice, and as carriers flow, right, how much hindrance the lattice is providing to the carrier flow. Now, if you increase temperature, the lattice also vibrates, and you have a lot more hindrance, and hence your resistivity can change. Now, if it's a semiconductor material, right, so it is possible that with temperature increase, the resistivity decreases, because you kind of have more and more carriers. So, for example, if you have a resistor, in some processes you get a resistor which are made of intrinsic silicon. So you will see that as temperature increases, the resistivity decreases. The resistance, in fact, decreases. They have negative temperature coefficient. But in most cases, even if you are using N-well resistor or polysilicon resistor, you will see that as you increase the temperature, the resistivity increases. Right? So now, I mean, how do you go about then designing a resistor? So typically, it's longer than, I mean, if you want a very big resistor, you make it a long wear, right? But again, just like in case of capacitors, in case of inductors, you do not want to, or in case of just like you have in case of MOSFETs, you do not want to make a very long resistor, simply because one of the reasons you do not want to make a long, so let me first draw a long resistor, then probably it will make sense. So this is L. Let's say I'm drawing a polysilicon resistor. This is L, this is W. You are getting signal from here, you are getting signal here. So one of the reasons you do not want to draw a very long resistor is because the value of the resistance itself can change if basically if you make it, let's say, a 100 micrometer long or a 200 micrometer long resistor piece of wire, then the doping concentration in a process can itself change, so that the value of the resistivity around this point, or the doping concentration of this point and doping concentration of this point, is not the same. So you might end up getting a different, when actually the chip comes out, you might end up getting a slightly different value of resistors that you normally get, right? So then what is the solution? You try to ensure that you break up the resistor into smaller pieces, right? You break up the resistor into smaller pieces, and you do the serpentine kind of structure. And so on, right? So that way you keep, I mean, you do not make a skewed dimension, you keep the dimensions close by. The second thing to take care is that you do not make a resistor which is square in shape, right? I mean, just because your technology allows, don't make a resistor like this, where you have a contact here, and you have another contact here and there, right? So maybe this is coming like this. Don't make a resistor like this, even though this is the W, this is the L. Right? Even though maybe by your calculation you find that you get a W. This squarish W by L is giving you the resistance that you desire. The reason being your contacts are not spread along everywhere, right? So what will end up happening is that the current will eventually flow from, it will obviously always take the least resistance path. The current will kind of flow from here to there and here to there. It will not take up the entire space that you have budgeted for it to flow. Correct. So you will invariably end up getting a higher value of resistance than you actually thought you would. But if you make a slightly longer wear, right, not long like hundreds and 200s micrometer, but if you make slightly longer wear, then the current direction, then when the current flows, you kind of get a symmetric current flow which encompasses the entire dimension or the width of the resistor. So in the resistor, the current flow can flow like this. It can go like this. It can go like this. It can go like this. And you kind of, the error that you have, that you kind of encounter because of the asymmetric distribution of current leading up to an error in the value of the resistance is minimized if you do that, right? And the other thing that you should take care, while if the very high frequency performance for a resistor is also important, you should be aware of the fact that these are all distributed resistances, right? So you will have, again, this resistor is also sitting on a substrate, so you are invariably going to have capacitance to ground. So effectively, no resistor is a resistor. The resistor is a distributed resistor. So when you are simulating or when you are taking up any PDK, if your resistance values are of importance, ensure that you simulate it once and see that it has frequency characteristics modeled, right? If it's just a resistor which is as good as an ideal resistor, that probably will not be able to capture many of the frequency effects that you might want it to capture, right? So again, having said that, when you are designing RF, if this were a data converter course, then probably I would have spent a lot more time talking about how to match two resistors, what are the things that you need to take care in order to ensure that two resistors are almost as identical as possible. But fortunately, in RF circuits, we are much more concerned about capacitors and inductors than resistors. Resistors are sometimes becomes sometimes they appear when they do not want them to, right? So the most of the course goes in mitigating those effects, right? So that's why I will not going to spend too much time on how to design a resistor, right? I mean, as it turns out, you put together some resistor, it's going to work in RF, right? So we are more concerned with inductors and capacitors, right? Okay, we'll stop here. Thank you.